Welcome to the lecture series on numerical methods. In this lecture series, we are just discussing this numerical differentiation based on interpolation. And in the previous lecture, I have discussed this differentiation based on this Newton's divided difference interpolation and this error differentiations. And in this lecture, we will just continue about this differentiation using this central difference approximations and some of this finite difference approximations, like based on finite difference operators. So, if you will just go for this error term analysis based on this Newton's forward difference formula. So, usually this error terms for this Newton's forward difference approximation is written in the form like Rn plus 1 x, this equals to omega x f to the power n plus 1 zeta by n plus 1 factorial, where this omega x is usually written in the form like x minus x0, x minus x1 to x minus xn here. And in terms of p, if you will just write, then it can be written in the form like p into p minus 1 up to p minus n h to the power n plus 1 and f to the power n plus 1 zeta by n plus 1 factorial here. Since usually we are just expressing p as x minus x naught by h, and that is why obviously we can just replace that one as in the form of p minus 1, p minus 2, that I have discussed in the previous lectures. So, this zeta value can be determined as minimum of x0 to xn, this should be lies between zeta, and maximum of x0 to xn here. So, if we want to differentiate this error term here, then this error term Rn plus 1 x can be written as Rn plus 1 dash of x, which can be expressed as h to the power, since it is the constant here, h to the power n plus 1 d by dx of p into p minus 1 up to p minus n f to the power n plus 1 zeta by n plus 1 factorial here, plus if you will just consider here plus h to the power n plus 1 d by dx of your f to the power n plus 1 zeta by n plus 1 factorial into the product of p terms here, that is p into p minus 1 up to p minus n here. Since zeta is a function of x, so that is why we have to differentiate this one with respect to x also here. So, if you will just go for this like elimination of process here, then we can just find that h to the power n, it will just come, since if you will just see d by dx, usually it can be written in the form of like d by dp into dp by dx. So, dp by dx, that will just give you 1 by h here, since usually we are just expressing x is as x0 plus ph here. So, that is why if you will just write this one as dp by dx here, which can be written as 1 by h here. Obviously, this differentiation can be replaced as d by dp of the total function p into p minus 1 to p minus n into dp by dx here. So, that is why this h term is coming, and the final representation, it can be written in the form of like h to the power n, if you will just write, into d by dp of p into p minus 1 up to p minus n f to the power n plus 1 zeta by n plus 1 factorial plus the remaining term. And if you will just apply this differentiation, since in the earlier lecture we have just derived this differentiation of f to the power n plus 1 zeta there. So, that is just completely expressed in the form of like divided difference form there. But here if we want to express this differentiation in the form of like Newton's forward difference operators here, then this forward difference operator can be replaced here this f to the power n plus 1 zeta as del to the power n plus 1 y0 by n plus 1 factorial here. Obviously, we can just express this one in delta form here, since in all of these lectures I have just explained that this tabular values is known to us, but the function is not known explicitly to us. So, that is why if this tabular values has been given to us, directly we can just approximate this error term by considering all of these tabular values, even if these differentiations can be approximated by using this forward difference table here. And if you just write this difference terms here in terms of Newton's forward difference operator, so this can be written in the form of like del to the power n plus 1 y0 divided by n plus 1 factorial into h to the power n plus 1 here. So, once it can be expressed in this divided difference form, sorry, this forward difference form here, then we can just obtain this f to the power n plus 2 zeta term, since you will, if you will just take the differentiation of f to the power n plus 1 zeta by n plus 1 factorial, so that will just give you f to the power n plus 2 zeta by n plus 1 factorial into zeta dash x there. So, that is why it can be expressed in the form of like del to the power n plus 2 y0 by n plus 2 factorial h to the power n plus 2 there. And obviously, if you will just write all these terms here, then this can be expressed as a d by dp of p into p minus 1 into p minus 2 up to p minus n del to the power n plus 1 y0 by n plus 1 factorial into h plus p into p minus 1 up to p minus n into del to the power n plus 2 y0 by n plus 2 factorial into h there. Since h to the power n plus 1 is there, and it can just cancel it out with h to the power n plus 2 and 1 by h is left over there. Since at x equals to x0, obviously we are just obtaining p equals to 0 if x equals to x0 there, and at that point we can just write this error terms differentiation, that is r plus 1 r of n plus 1 dash of x0, this can be written as minus 1 whole to the power n factorial del to the power n plus 1 y0 by n plus 1 factorial h here. Since if you will just see this expansion here, that is d by dp of p into p minus 1 to p minus n at p equals to 0 is nothing but minus 1 whole to the power n factorial here. And that is why they say Rn plus 1 dash x0 can be written as minus 1 whole to the power n del to the power n plus 1 y0 by n plus 1 into h also sometimes. Since n plus 1 factorial, it just take the product of n factorial into n plus 1, so that is why n plus 1 remained over there. So, based on this error approximation, so we will just go for a computation of error in the Newton's forward interpolation formula. So, for that, if you will just consider a table like x is prescribed at 2, 2.20, 2.40, 2.60, 2.80 and 3.00 here, and corresponding y values, if it is just given like 0.6932, 0.7885, 0.8755, 0.9555, 1.0296, 1.0296 here, then the first differences if you will just compute here, that is as the difference of 0.7885 minus 0.6932, since already we have derived a lot of this forward difference approximations in the tabular form. So, that is why it is easy to compute, since we will just consider this difference of like two values corresponding tabular values associated to each other there. So, 0.7885 minus 0.6932, this just gives you the values as 0.0953. Difference of 0.5755 minus 0.7885, this is just giving you the values as 0.0870. The difference of these two values 0.8755 minus, sorry, this is 0.9555 minus 0.8755, this is just giving you 0.0800. Then 1.0296 minus 0.9555, this is just giving you 0.0741. Then the difference of 1.0986 minus 1.0296, this is just giving you 0.0690 here. Similarly, we can just obtain the second differences here, third differences and fourth differences. So, based on this, if the tabular point is asked to compute up to third differences and then obtain this error term, then we obviously we can just write this one as the fourth term there, since the divided difference up to third order can be approximated in a polynomial form there. Immediate next term can be considered as the error term for that position. Therefore, the error term can be written in the form like R4 of x here. So, usually this R4 of x0, it can be written in the form of like if you will just see here, R4 of x can be written as like omega x f to the power 4 of zeta by 4 factorial. So, especially it can be written if you will just write in a complete form here. So, R4 of x can be written as omega of x f to the power 4 of zeta by 4 factorial here. And in a differentiation form, if you will just write R4 dash of x, this can be written as minus 1 whole to the power n, that is n equals to 3 there, and then we can just write del to the power 4 of y0 by n plus 1, this means n is 3 here, so 3 plus 1 into h here. So, obviously if you will just put directly in the tabular values here, so R4 dash of x0, this can be written as minus 1 whole to the power 3 del to the power 4 of y0 by 4h here. And at that point exactly, if the error is asked, suppose at x0 equals to 2.00 here, since the beginning of the tabular values is 2.00 here. So, R4 dash of 2.00, it can be written as like minus 1 whole to the power 3. So, that will just give you a minus sign here, and this your h size is like 0.20 here. So, that is why minus 1 by 0.20 into 1 by 4 into your del to the power 4 value, that is just giving you minus 0.002 here. So, obviously if I will just write here, this can be written in the form of like absolute values of minus 1 by h into 1 by 4 into del to the power 4 of y0 here, and this is nothing but minus 1 by 0.20 into, since this value is just giving you like minus 0.0002 here by 4. So, this can be written in this form here, and obviously this value is just giving you 0.00025 here. So, if you will just define this like differentiation using like finite difference operators. So, finite difference operator means we can just consider that shift operator here. Shift operator is usually expressed in the form of E of f of x here. So, E of f of x is usually written in the form like f of x plus h here, and f of x plus h can be expressed in the form of Taylor series as h d of f of x h d whole square by factorial 2 f double dash of x plus rest of the terms, and usually it can be represented as 1 plus hd plus hd whole square by factorial 2 plus this one into f of x here, and obviously it can be written in the form of e to the power hd f of x here. And finally, we are just expressing this shift operator e as e to the power hd here, that we have just expressed in the earlier lectures, that d equals to d by dx here, that is nothing but the derivative here, and which can be expressed in the form of like forward difference operator, backward difference operator, central difference operators. In any form we can just express this shift operator. So, based on that we can just say that these operators can also be expressed in the differential operator form also there. That means that d by dx can be expressed in the form of like delta, nabla, or central difference operators like small delta, and average operators like mu there itself. So, if you will just express these differential operators in the form of like forward difference operator, like first difference if you will just consider for this Newton's forward difference operators at a point k, then we can just write h d of f of x k can be expressed in the forward difference form as del of f of x k minus half del square of f of x k plus 1 by 3 del q of f of x k minus up to finite number of terms. Similarly, this differential operator can also be expressed in a backward difference form, that can be expressed as nabla of fk plus half del square of fk plus 1 by 3 delta q of fk. So, likewise we can also express, and also in central difference approximations this can be written as delta of fk minus 1 square by 2 square 3 factorial delta q of fk plus 1 square into 3 square by 2 to the power 4 5 factorial delta to the power 5 fk. So, likewise we can just express this differential operators in various operator form. So, the same way also we can just express this second order differentiations also. This means that second order differentiation we can just consider that one as h square f double dash of xk, and this is nothing but hd you can just write. So, hd can be written as again one more differentiation we can just consider this expansion of Newton's forward difference operators, backward difference operator or the central difference operators. So, if you will just consider this operators once more here, this can be expressed as del square of fk minus del q of fk plus 11 by 12 del to the power 4 of xk for forward difference operators. Similarly, we can just express this one in a backward difference operator, that is in the form of nabla square fk plus nabla q fk plus 11 by 12 nabla to the power 4 of fk plus all other terms. And in a general form, if you will express this one as h to the power r d to the power r here. So, this can be expressed as del to the power r minus half r del to the power r plus 1 plus r into 3l plus 5 by 24 del to the power r plus 2 minus all other terms are there. Similarly, if you will just take this backward difference operator, that it can be expressed as nabla to the power r plus half r nabla to the power r plus 1 plus r into 3r plus 5 by 24 nabla to the power r plus 2 plus all other terms. And if you will just use this central difference operator to express this rth order derivative of any function, then it can be expressed as small delta to the power r minus r by 24 small delta to the power r plus 2 plus r into 5r plus 22 by 5760 small delta to the power r plus 4 minus all other terms, it can be expressed up to finite number of terms. So, next we will just go for central difference approximation, how we can just use these differentiations for central difference approximation like Stalling's formula and Bessel's formula here. For the Stalling's formula, already we have derived this expression for Stalling's formula, that is expressed in the form of the central difference approximations for Stalling's formula. Usually it is written in the form of yp or y of x or y of xp, can be written as y0 plus p mu delta of y0 plus p square by 2 factorial delta square of y0 p plus 1 3 mu delta q of y0 plus all other terms are there. So, if you will just differentiate with respect to x here, that can be written as dy by dx, this as 1 by h, since usually this expression can be written in the form like dy by dp into dp by dx. So, that is why dp by dx is nothing but 1 by h, and d by dp of your expression y0 plus p mu delta of y0 plus p square by 2 factorial delta square of y0 plus all other terms are there. If you will just differentiate this one with respect to p here, this can just give you 1 by h, first term it will just give you 0, second term mu delta of y0 here plus 2p by 2 factorial, so p delta square of y0 plus the third factor, if you will just take this one, that will just give you 3p square minus 1 by 6 mu delta q y0 plus all other terms. And if you will just take one more differentiation of this scheme here, that is d square y by dx square, it can be written as 1 by h square. So, first term is just treated as a constant here, then it will just start from this immediate next term. So, del square of y0 here, so 3 into 2 into p here. So, 6 by 6 cancel it out. So, that is why it can be written as p mu delta q of y0 plus rest of the terms here. Similarly, we can just use this formulation for like Bessel's formula here. So, Bessel's formula usually it is expressed as like yp equals to y of xp, that as mu y of half here. So, if you just write this one as yp in Bessel's formula here, this is for Stirling's formula here. For Bessel's formula, usually this yp is written in the form like mu y of half plus p minus half delta y of half here plus p2 mu delta square y of half plus p2 p minus half by 3 delta q of y of half here. So, plus all other terms. If you just take the differentiation here, the same form we can just write dy by dx, this as 1 by h. The first term we can just take here as like delta y of a half here. So, then plus 2p minus 1 by 2 mu delta square y of a half, then 6p square minus 6p plus 1 by 12 mu delta q of y of a half plus all other terms there. Similarly, if you will just take this second differentiations here, that can be written in the form of 1 by h square mu delta square y of half. Since if you will just take the differentiation of second term here, since first term is constant here, second term if you will just take, that can be represented as mu delta square of a half here plus 6p square means 12p minus it is like 6 here. So, that is why 2p minus 1 by 2 delta q of y of half plus all other terms we can just write. So, based on this, if you will just go for an example here, since central difference approximations usually it can be approximated at center of the table here, where for both of these formulas we have defined this approximate parameters, so that where it can be used. So, in that regard, if you just consider this table as like x is defined at 1.00, 1.50, 2.00, 2.50, 3.00, 3.50, all are equispaced points with space size 0.5 suppose. With this corresponding y values as 1, 1.1447, 1.2599, 1.3572, 1.4422, 1.5183 here. Then if you will just use this first differences for all these values, we can just obtain this one as 1.1447, sorry 0.1447, 0.1152, 0.0973, 0.0850, 0.0761 for first differences. For second differences, if you will just take the differences of immediate next terms, 0.1152 minus 0.1447 here, then that will just give you minus 0.0295 here. Similarly, if you will just take the difference of 0.0973 minus 0.1152, this will just give you minus 0.0179 here. And if you will take the difference of 0.0850 minus 0.0973, this will just give you minus 0.0123 here. If you will just take the difference of 0.0761 and 0.0850, that will just give you minus 0.0089. Similarly, we can just define this third difference, fourth differences and fifth differences here. Since we have here 6 points, so that is why you can just consider the differences up to fifth order here. And if it is asked to use this Stirling's formula and Bessel's formula for this error approximation up to suppose third order term here. So, up to third order we can just consider, and immediate next term we can just consider the error form here. First we have computed these derivatives at that values, like suppose the value is asked to compute this derivative at 2.40 here. So, that is why we can just put here y dash x is defined as 1 by h mu delta of y0 plus p delta square of y0 plus 3p square minus 1 by 6 mu delta q of y0 here. So, that is why we can just use h is 0.5 here, 1 by 0.5. So, average of these two this is like mu delta can be written as your values, we can just write delta y of 1 plus delta y 0 by 2 there. So, that is why it can be written as 0.0973 plus 0.0850 by 2 there. Directly you can just express in the form of if we want to write this one as mu delta here. So, mu delta can be written as e to the power half plus e to the power minus half by 2 into e to the power half minus e to the power minus half here. If we will just take the product here, we can just obtain this one as e minus e of minus 1 by 2 here. So, obviously we can just write this one as f of x plus h minus f of x minus h by 2. So, that is why we are just using this differentiation, if you will just see, as 0.0973 plus 0.0850 here by 2. So, using all this we can just obtain this values as 0.1866 here. The second order formula if you will just use here, that is y double dash of x here. So, y double dash of x, it is just given as 1 by h square delta square of y 0 plus p mu delta q of y 0 plus all other points. So, similarly h is given as 0.5 here. So, that is why 1 by 0.5 square here we have considered, and delta square of y 0, that is nothing but the second order differentiation of this central this forward difference table also. So, that is why it can be considered as minus 0.0123 here, plus p value that is given as minus 0.2 into the average of delta q values we have just considered here, and the rest of the values can be defined in the same form here. And finally, we are just obtaining y double dash of 2.40 as minus 0.0518 here. And if you just use this formula for the point 2.80 here, then we can just use Bessel's formula for that, since p range is lying between 0.25 to 0.75. Within that range, especially we can just use Bessel's formula. So, for that, if you will just find here, the derivative of y of x is usually written as 1 by h delta y of half plus 2p minus 1 by 2 mu delta square y of half plus 6p square minus 6p plus 1 by 12 mu delta q y of half here. So, if you will just put these values like 1 by 0.5, 0.0850 plus 2 into 0.6 minus 1. So, all other terms it can be placed accordingly. Then we can just obtain this first order derivative at 2.80 as 0.1676 here. So, the second order formula if you will just use here, that is in the form of 1 by h square mu delta square y of half plus 2p minus 1 by 2 delta q y of half. So, then we can just obtain at the point 2.80 as, since already we have obtained that h as 0.5 here. So, that is why this can be written as 1 by h square means 1 by 0.5 whole square. So, then mu delta square y of half, if you will just take mu as the average value here. So, delta square half we can just write this one as delta of y of half, and we can obtain the values in the form of minus 0.089 minus 0.0123 divided by 2 here plus 2p minus 1. So, p is given as 0.6 here, 2 into 0.6 minus 1 by 2 into delta q y of half. This is nothing but directly we can just obtain from this divided difference formula here, this forward difference formula, and the final value is obtained as minus 0.0410 as this one. Thank you for listening this lecture.